Okay. Yeah. Very good morning, my dear students. In the last class, we were just discussing regarding the three important terms. One is called shear stress and shear strain, and then the volumetric strain, bulk modulus, and also we discussed generalized Hooke's law. So let me just refresh the things what we have discussed in the yesterday's class quickly. So we discussed shear stress and shear strain. So we have the sign convention for shear stress and a shear strain when we take a positive shear stress and when we take a negative shear stress. When the shear stress is making the moment which causes the body to rotate in the clockwise, we take it as a positive shear stress, and shear stress which results in the anti-clockwise movement or movement of the rotation of the body, we call it as a negative shear stress. So the ratio of shear stress to shear strain will remains constant. So that is what that constant value, what we term it as a modulus of rigidity or rigidity modulus or shear modulus, right? So we define rigidity modulus or shear modulus as the ratio of shear stress to shear strain, right? And then of course the unit of rigidity modulus and will remain same as that of the modulus of elasticity, that is Newton per millimeter square, or in pascals or gigapascals and gigapascals. And we generally denote the modulus of rigidity by a letter called G. Right? This is what I just taught it in the yesterday's class. And later onwards, we just move on to the generalized Hooke's law, where the what we call it as the when the body is subjected for stresses in all the three mutually perpendicular directions. So by making use of a Hooke's law and the principle of superposition, we can easily determine what is the strain along the each direction. Okay, so using that, I think we have discussed how we can obtain a net strain along individual axes X, Y, as well as Z axes. And also we have written the table. So how the net strain can be calculated for a body which is subjected for stresses along all the three mutually perpendicular direction, right? So that is what we were just discussed. And also I think I just started with the volumetric strain. So what is volumetric strain? The change in volume to the original volume. Okay, we usually denote volumetric strain as epsilon suffix V. Okay, and also we discussed what is volumetric stress, the stress which causes the change in the volume, says change in the volume but not the shape. So that condition or the state of a stress, we call it as a volumetric stress, and the ratio of volumetric stress to the volumetric strain remains a constant, and that constant we call it as a bulk modulus, right? So bulk modulus is the ratio of volumetric stress to the volumetric strain, and it is denoted by a letter called K, and it is also having the same unit as that of the modulus of elasticity, that is Newton per millimeter square or Newton per meter square. Okay, I think this is what we just stopped in the last class. Let me just continue with the same thing today. In today's class, so we have two important derivations to do. One is the volumetric strain in a rectangular bar, and later part I will take you for the establishing a relationship between the modulus of elasticity and the modulus of rigidity. So this is a very important derivation from the examination point of view, to establish a relationship between the elastic moduli, that is a modulus of elasticity and modulus of rigidity. So that is two important derivations. We will go into do it in today's class, and later at the end of the class. So today, instead of a multiple choice question, you have a one short answer to be written. So short answer in the sense, I have given one assignment question. That assignment has to be written in a sheet of paper, and the same thing has to be posted in the Google Classroom. Okay, so please keep it a sheet of paper and a pen with you. So one simple question I have asked. So instead of a quiz, so we have an assignment question. So assignment question number 2, this is today. Simple derivation I have asked, so that you have to do it and you have to post it within the Google Classroom. Okay, so that is what at the end of the class, instead of a quiz, the task what you're supposed to do it. Right, let us start with the class today. So today Yeah. So volumetric strain in a rectangular bar. Let us take this in today's class. So let us consider. So yesterday we discussed volumetric strain. Volumetric strain is the ratio of change in volume to the original volume. Am I right? So now, so how we can determine or how we can express the volumetric strain when in the case of a rectangular bar. Okay, so for this, we have considered a rectangular bar of dimensions L, capital L, width B, and depth D. So which is as shown in the figure. Okay, so this is a rectangular bar having a width length L, width B, and depth D, right? So now in this case, what is the volume V of the bar is? How do we write the volume of a bar? V is equal to L into B into D. So we know volume is the product of length into width and the breadth. So this is what we have written here, L into B into D. Right. Now to write an expression for a volumetric strain in this case, so what we do here is we will take a partial derivative of the above equation. So what happens here? Delta V is equal to delta L into B into D plus delta B into B D into L plus delta D into L into B. So just taking the partial derivative of the above equation. And later part, we are dividing the entire equation by V, volume V. Okay, so when you divide this by V, so what happens on the LHS side? Delta V divided by V, which is equal to this first term, delta L into B into D. If you divide this by V, so V is nothing but L into B into D. Am I right? So L into B into D, if I write over in the denominator for this term, so B into D, BD will going to be gets cancelled and the remaining term in the denominator will be L. So therefore, the first term will becomes delta L by L. Am I right? Plus, moving on to the second term, same thing over here. When you divide this by V, which is equal to L into B into D, so D into L will get cancelled. The remaining term will be B. So therefore, delta B by B, you will going to get it. Plus third term, delta D into L into B and divided by volume. So the resulting expression will be delta D by D. So this is the expression what we will going to get it. So when you divide the partial derivative of the volume of a bar by means of a volume V. Okay, so on the LHS side, I will keep V only instead of substituting it as L into B into D. I will keep it as V only. So now look at the LHS part. So LHS part, it is the ratio of delta V by V. Delta V is nothing but the change in the volume, right? Change in the volume to original volume. So what does it mean? The change in the volume to the original volume, it is nothing but what we defined it as a volumetric strain, right? So therefore, so on the LHS side, we can express or we can write delta V by V as an epsilon V, which is nothing but a volumetric strain. So now this LHS will become volumetric strain epsilon V. Now moving on to the RHS terms over here. So look at the first term here, delta L by L. What is delta L by L? It is the strain in the X direction because L is the dimension in the X direction. So therefore, delta L by L is nothing but the strain. We can say it as a strain in the X direction. Similarly, delta B by B. So this is a strain in the Z direction. Okay. And of course, delta D by D, which might be a strain in the Y direction. Okay, so therefore, what happens? This entire expression can be expressed in terms of a strain, which we will going to get it as epsilon V is equal to epsilon X plus epsilon Y plus epsilon Z. This is a very important relationship for us. Epsilon X plus epsilon Y plus epsilon Z, the sum of the three strains in the X, Y direction, which is will be equal to epsilon V. Okay, this is nothing but the volumetric strain what we have, right? So this is the very important conclusion at this point. So where the volumetric strain is the sum of the strains along the x, y, and z directions. Okay, so this is what we call that as the volumetric strain is the sum of the strains in the three mutually perpendicular directions. So please remember this. This is a very important derivation and very important conclusion what we are arriving at. Okay, so epsilon V, the volumetric strain, is the sum of the net strains. We can term it as a net strains along x, y, and z directions. Is it clear, my dear students? Any clarification till now? Akash?
No, sir.
Any clarification? How to get a volumetric strain
No,
in a
sir.
rectangular bar? Understood?
Yes, sir.
Manu Hariharan? Manu?
Yes, sir. Yes, sir. Understood, sir.
Understood. Manu,
Yes,
you
sir.
had to log in with your official mail ID. You are logged in with some other mail ID. I'm just getting that information.
Sure, sir.
You have to log in with your official mail ID only. Okay?
Okay, sir.
Right.
Yes, sir.
Madhu?
Sorry.
Madhu, understood?
Yes, sir.
Okay. So any clarification, my dear students? Because at the end of today's class, you have one assignment question. So you have to solve that and you have to write it in a sheet of paper, scan it, and you have to post it in the Google Classroom. So please understand derivation of a volumetric strain in a rectangular bar. Okay. So this is the expression what we have got for a volumetric strain in a rectangular bar. Any clarification, my dear students? Anybody you can ask. If you don't have any clarification, I will just proceed. Should I proceed, my dear students?
Yes, sir.
Right. Okay, done. Now, with this derivation, with this conclusion, so that is epsilon V is equal to epsilon X plus epsilon Y and epsilon Z. So now let us assume that that block is being subjected for three mutually perpendicular stresses, or in the sense stresses in all the three mutually perpendicular direction. That is along X direction, along Y direction, along Z direction. If that is the case, so how we can calculate or how we can determine the volumetric strain in that rectangular bar, which is under the subject to stresses in all the three mutually perpendicular stresses. Okay, this is another one important conclusion what we are arriving at. Right. So this you can understand. See why yesterday what I have just showing here. So like this, just take this block. So now let us take this block is been subjected for the stresses sigma x, sigma y, and sigma z in all the three coordinate axes. So the normal stresses, a body subjected for normal stresses along the coordinate axes whose stresses are sigma x in the x direction, sigma y in the y direction, and sigma z in the z direction. Okay. So now what we want here is we want to write an expression for a volumetric strain in this condition. In the sense the body under the state of a stress in three mutually perpendicular direction. So how we can write that one? This is a very important thing for us. Why? Because so we are arriving at one important conclusion now. So another one important expression we will going to get it over here. So what is that expression? So we will go into see, right? So now, so let us assume that let us take the bar is subjected for stresses. A rectangular bar is subjected for stresses along sigma x, sigma y, and sigma x and y directions respectively. Then we know volumetric strain is the sum of the net strains along three mutually perpendicular directions. Am I right? So now, by using a generalized Hooke's law, so generalized Hooke's law, we can write the volumetric strain as, see, this is the important conclusion what we have arrived. So how we have done here is, So volumetric strain is epsilon x plus epsilon y plus epsilon z. So this is the sum of the net strains along x, y, and z directions respectively. This is the volumetric strain is a sum of net strains along x, y, and z directions respectively. Now, we know how to write a net strain, an expression for a net strain in the individual axes, considering the effect of each stresses in that particular direction. Am I right? So this is by using a generalized Hooke's law. So by using generalized Hooke's law, we can write what is the net strain acting along x, y, and z direction. I think in the yesterday's class, we have prepared a table and I have just given what is the expressions for the net strains along x, y, as well as the z direction. Let me just go back to that table. Yesterday, what I discussed. Yeah, this is a table what I am talking over here. So this is the net strain. So net strain along x, y, and z axes. So we have got this expression. So strain along x-axis, strain along y-axis, strain along z-axis. So this is, I think yesterday we have discussed this. I think everybody could be able to understand how we can arrive at this equation in the yesterday's class. So f sigma x by E minus nu into sigma y by E minus nu into sigma z by E. So this is the net strain expression for an along x direction. In the similar way, we have for y direction. Along y direction, this is the expression what we have. And along z direction, this is the expression what we have. So now what we have to do here is, so in the expression for a volumetric strain, that what we have shown it as an epsilon x plus epsilon y and epsilon z. So we have to substitute these equations over here. These equations we need to substitute over there. So after substituting, we have to get the expression for the final expression for the volumetric strain. So how we can do that? Yeah. So now substitute all those expressions over here, right? So then later you can get the things that done. So I want you people to quickly, I want everybody to do this. So epsilon v, you have to get this expression. Substituting, just a minute. Substitute sigma x as this expression, sigma y as this expression, and sigma z as this expression. Okay, so please make that. So add all these three equations and simplify, and you're supposed to be getting this equation finally. Please check. Just I will give just 2 minutes time for you people to complete that task quickly. I want everybody to do that in a sheet of paper and do that. Okay, hope I think you people will be able to do this. So this is the final expression what we will going to get. Volumetric strain in a rectangular block subjected to the three mutually perpendicular stresses or stresses in three mutually perpendicular directions is given by sigma x plus sigma y plus sigma z divided by E into 1 minus 2 nu. Yeah, okay. So I think I will just move into this. So this is the final expression you're supposed to remember. So volumetric strain is equal to sigma x plus sigma y plus sigma z divided by E into 1 minus 2 nu. Please remember this and please make a note of this expression also, okay? Because in the future you might to use this expression in for derivation. Okay, right. Is it clear, my dear students? Any clarification? Is it clear, everybody?
Yes, sir.
Okay, right. So this is the one important derivation what I supposed to express for you. Now, let us move on to the very important derivation now, that is to establish a relationship between the modulus of elasticity and the modulus of rigidity. Please make a note of this. This is a very, 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 very important derivation from the examination point of view. Okay, quickly I will take you this. Okay, so if you have any clarification at any moment, you can stop me. Right. So now, yeah. Till now we were discussing the concepts of modulus of elasticity, modulus of rigidity, and bulk modulus. And of course, we also discussed the Poisson's ratio. In today's class, we will establish a relationship between the elastic constants, elastic moduli we can call it as. So the first derivation what we will going to establish, or relationship what we will going to establish, is the relationship between the modulus of elasticity E, modulus of rigidity G, and the Poisson's ratio nu. So making use of this, we will go into derive an expression. Okay. So now let us take, just a minute. Yeah. So let us consider, the relation between the elastic constants. So I have written it as a relation between E, G, and nu. Okay. Now let us consider a cube of material of side A. So A is the side of this cube. I think cube you can understand. Cube is the one which is having all sides equal. Okay. And subjected to an action of shear and complementary shear stresses and producing the deformed shape as shown in the figure. So it has been subject for shear stresses over here. Okay. So now this is the a cube which is having initial, it is a straight. Now because of the application of a shear stress or the application of a shear load, it has been changed its state from A to C. A to C. The diagonal, initially the diagonal of the cube was OA. Now because of that it has become OC. Okay. So now, and of course, so little of geometrical construction supposed to be done over here. So since the A has been moved to the point C, okay, so we will go into drop a perpendicular AB, drop a perpendicular AB to OC, okay, to OC. So this ABC is 90 degrees. So please remember this, the angle ABC is 90 degrees. And because of the deformation, because it has been subjected for a shear force or a shear stresses, so it will be undergoing a shear strain that is given by phi. Okay, phi represents a shear strain and tau represents a shear stress. Right. So this shear strain is A. So this angle, this level represents the shear strain in this case. Is it clear? The diagram is clear. This is a very important diagram. Please consider a cube of material of side A, and it has been subjected for a shear stress tau. And because of the shear stress, so the diagonal OA has been shifted to, means point A has been shifted to point C. So the diagonal initial previous diagonal, original diagonal was OA. Now the new diagonal is OC. Okay, so it means the length of the diagonal has been increased because of the application of the shear stress, isn't it? So now this is a diagram and simple construction. So drop a perpendicular AB on OC. Okay, and let the phi is a shear strain, isn't it? Now let us take to, since the within the elastic limits the strains are very small, the angle ACB may be taken as 45 degrees. So this angle I am talking about, ACB. So this is 90 and this is 45. Okay, this ACB, because strains are very, very small within the elastic limit. So therefore the angle, that is angle, this angle ACB, we will going to take it as 45 degrees. Okay, now let us move to the next slide. Since the angle between OA and OB is very small, okay, OA is almost equal to OB. So this is what they say, OA is equal to OB. So because the strain is very small, the length, that is OA, will be equal to OB. Okay, next. Now we want to write the change in the length of the diagonal OA. See, initially, before the application of a shear stress, the length of the diagonal was OA. Now, because the application of a shear load or a shear force, the length of the diagonal OA has been changed to OC. In the sense, there will be a strain. The deformation is taking place in the diagonal OA, or there will be a change in the length of OA. So which is how we can calculate the change in the length of OA. So that is what we will going to discuss it now. So if you find any clarification, you can stop me. Okay. Strain on the diagonal OA is equal to change in length by original length. Change in length by original length. This is how we will going to calculate. So what is change in length? How much amount of change has been occurred? It is BC. Am I right? I told you already. OA is equal to OB because the strains are very, very, very small within the elastic limit. So we have assumed it as OA is equal to OB. So how much amount of strain has occurred? How much amount of change in length has occurred is nothing but BC. Okay. So BC is the change in length and the original length was OA. Am I right? Now, how we can express BC? Yeah, now let us move on to the diagram over here. BC, I want BC. Okay, so how we can write this BC? So if I take this angle as 45 degree, so ACB is a 45 degree. Am I right? So if I take cos phi, cos 45 is equal to what? Which is nothing but BC by AC. Am I right? Because adjacent side by hypotenuse. So I can write this side BC in terms of the cos 45. So I have already told the strain is very small. The angle ACB is 45 degrees. So now this is 45 degrees. So 45 degree is nothing but the cos 45. If I write the cos 45 for this, it is the adjacent side divided by the hypotenuse. So now what I want is BC. Am I right? So BC can be written as AC into cos 45. Can we write like this? BC is equal to AC into cos 45. That is why we have written here So in this diagram, in this expression, instead of BC, we have written it as AC into cos 45. Right? Next comes OA. This is OA. So how we can write OA? OA, we want OA, this one. So this can be expressed in terms of, see, this OA, this is 90 degree. Okay, this will be 45 degrees. So 45 degrees means what happens here? So OA, I want it is a hypotenuse. Am I right? So OA is equal to, if I take sine 45 anywhere, it is nothing but what we will going to get. Just a minute. Yeah, it is nothing but if you take anywhere, whether it is 45 here or 45 here, whatever it might be. So sine 45 will be equal to opposite side, which is nothing but the A, small a. Am I right? Small a is the side A divided by OA, hypotenuse. Sine 45, opposite side by hypotenuse. So what we want is OA. So OA is equal to A divided by sine 45. Okay, so if you take 45 here also, this will be A only. If you take 45 here also, this will be A only, not an issue. Okay, you can do like that also. So what we have done here is, so we have substituted OA as A divided by sine 45. Okay, so now what we have here is AC into 2A, we have got it. How we have got 2A? So we will going to get sine 45 divided by cos 45. So sine 45 by cos 45, it is a tan 45. Tan 45 is 1 by root 2. So we're going to get 2A. Root 2 into root 2. So it is nothing but 2A. Am I right? 2 into A. So therefore, so AC, how we have got AC here? So please understand here. AC, we want this AC. How we can write AC as tan phi? What is tan phi or phi? Phi is the opposite by adjacent. So A phi is equal to AC divided by A. Okay, so in place of AC, I will write it as 5 into A. This is what we have done over here. Okay, please understand here. This is very simple geometry or trigonometry what we are doing here. So simplification of BC and OA. So finally, we are getting the strain along a diagonal is equal to 5 divided by 2. Okay, 5 divided by 2. So this is a very important conclusion what we have. It is found that strain along the diagonal is numerically half the amount of shear strain. Got it? Yeah. Next thing is, so once you get that one, so where strain along OA is equal to, that is epsilon OA is equal to 5 by 2. Now we know what is rigidity modulus. So we know rigidity modulus G is equal to tau by 5. Am I right? That is what yesterday we defined. It is a shear stress by shear strain. So now what we have got, the strain along diagonal OA is equal to, so we have got phi is equal to what? It is nothing but strain by 2G. Am I right? So strain by 2, I'm sorry, it is a shear strain by 2, what we have got, right? So what we are doing in this expression, in this step here is, so the strain along diagonal OA, which can be written as, so instead of phi, instead of shear strain, so if I take shear strain here, it will become tau by G. Am I right? It will become tau by G. So now tau by G means, so we're going to get strain along diagonal OA will be tau divided by 2G. Am I right? Is it right? Everybody could able to understand this? Any clarification, my dear students, anywhere? Because it's very important. Very, very, very important for us. Any clarification anywhere? You can stop me. Okay?
Yes, sir.
Okay. So now we have got strain along OA as tau by 2G. Right? the shear stress system is equivalent or replaced by system of direct shear stress, whatever shown in the figure. So now what happens? So this is the one important expression what we have got. Strain on the diagonal OA is equal to tau by 2G. So you take this equation 1. Now what happens? So if you take an element across, so if I take along OA, if I take any small elements, very small element along OA, okay, so what happens? So since you are applying a shear stress or if you're applying a shear load, the strain along OA or the stress along OA will be tensile in nature. And what happens along the another one diagonal, it will be compressive in nature. So this is what they have shown over here. See here. So along OC or along OA, it is sigma 1 is a tensile. Whereas along another one diagonal, in the opposite diagonal, opposite direction, it will be subjected for a compressive stress. One side is it is stretched, one side it has been compressed. So in the sense, there are two stresses acting. One is along the diagonal OA, which is tensile in nature, and another one is perpendicular to the diagonal OA, which is compressive in nature. So therefore, we have say, see sigma 1 is acting in this direction, which is positive, whose magnitude is equal to positive shear stress tau, and another one side, so the element is subjected for a compressive stress sigma 2, which is a negative tau. Is it clear, my dear students? Now the element is subjected for the stresses in the x direction and stress in the y direction. So stress in the x direction is a positive and stress in the y direction is negative, whose magnitude will be equal to tau only. So now what we have to do is we have to write what is the strain along OA, diagonal OA, by using the generalized Hooke's law. So this is what we have done in the next slide over here. Strain along OA due to direct stress. So please understand over here, strain along OA due to direct stresses, which is equal to, you can see here, sigma 1 divided by E minus mu into sigma 2 divided by E. See, this is the expression how we have got is, this is by using a generalized Hooke's law. Okay. So yesterday, I think I discussed generalized Hooke's law for the block subjected for 3 mutually perpendicular stresses. But in this case, only 2 direction stresses are there. So therefore, you can see sigma 1 and sigma 2. Sigma 3 is not there. So sigma 1 is acting along OA and sigma 2 is acting on the opposite to the or perpendicular to the direction of OA. So this is the expression what you can see, which you can arrive by using generalized Hooke's law. Okay. So now we have sigma 1 and sigma 2, which is equal to tau. So sigma 1 is a positive shear stress, where sigma 2 is a negative shear stress. So substituting sigma 1 and sigma 2 as tau with their corresponding sign. So we can say tau by E plus nu into tau by E. So how we have got positive here over is already minus. So sigma 2 is minus of tau. So you can see in the previous slide here. So you can see sigma 2, I have taken it as a minus tau because it is compressive in nature. Okay. So now substituting that, so we will going to get tau by E plus nu into tau by E, which we are going to take tau by A as a common term. You are going to get 1 plus nu. So this is strain in a diagonal OA due to direct stress. So you take, this is equation number 2. Now equate this equation 1 with equation 2. Equation 1 was what? Tau by 2G, and equation 2 is what? It is tau by E into 1 plus nu. So on the LHS side, you will going to get tau by G, 2G, and on the RHS side, you will going to get tau by E into 1 plus nu. So tau will get cancelled, and rearranging the terms, you will going to get E is equal to 2G into 1 plus nu. This is a very important relationship between modulus of elasticity and modulus of rigidity in terms of Poisson's ratio. So please remember, E is equal to 2G into 1 plus nu. where E is the modulus of elasticity, G is the modulus of rigidity, and mu is the Poisson's ratio. Is it clear, my dear students? Any clarification anywhere you can ask? You have to practice this. Unless you practice, it is not so easy to do this. Okay. So if you have any clarification, I will post this video in your Google Classroom. Sit at home and look at the derivation, practice it number of times, then things will be easy for you. Any clarification to anybody at this moment? You can ask. Anybody have any clarification, my dear students, with this derivation?
Sir, can you show the previous slide, sir?
Yeah, I will show. This one, huh?
Yes, sir.
Yeah, tell me.
No, sir, I had to just write the values.
Sorry.
I had to write these points, sir. That's why.
Okay. Note down.
Done, sir. Thank you, sir.
Okay. Anybody has got any clarification, my dear students? So because I had to go for one assignment question now. So if you don't have any clarification, I will give you the assignment question. Note down that question, and you have to simple derivation, simple task I have given, and you can do that, and you can post it in the Google Classroom. Shall I move?
Yes, sir. Continue, sir.
Okay, right. So take down this question. Everybody has to note down this question, answer it, and you have to put it in the Google Classroom. Show that volumetric strain in a bar having circular cross section is equal to sum of twice the diametral strain and longitudinal strain. So this is the mathematical expression what we supposed to get. Epsilon V, which is a volumetric strain, which is equal to 2 times epsilon D corresponds to diametral strain plus longitudinal strain. So this is the circular bar having a length L and capital small d as a diameter. Okay, I think today's first what we discussed is a rectangular bar. So rectangular bar, I explained how to calculate the volumetric strain. Okay, so you have to write the volume. I will give you just procedure: volume and partial differentiate and then divide it by V. So the resulting expression will be the volumetric strain. This is what you're supposed to do it now. Okay, so hint I given: volume of a circular bar or a cylinder is pi by 4 into d square into L. So this is the expression for a volume of a cylinder. This is clear, my dear students. Any clarification about this question? I want, and you have to prove this. Epsilon V is equal to 2 into epsilon D plus epsilon L, where epsilon D is the diametral strain and epsilon L is the longitudinal strain. Okay, so please do this, and I will go into assign this in your Google Classroom, and you can just Yeah, it is assigned as assignment question number 2. Assignment question number 2. So please do that and submit it within 10:30.